this lesson we're looking at thermodynamics, and it would be really useful if you were to look at the previous lessons on gas laws and kinetic theories before starting or attempting this one. Okay, we're going to use exactly the same experiment we used before, in that we're going to have a cylinder with a plunger attached to it, and that plunger can move back and forth, back and forth. We talked about before that if I were to move that plunger in, then of course the volume is going to decrease and the pressure will increase. And the things that we kept constant here were the temperature and the number of particles. This in effect is Boyle's law. So if we were to plot the pressure in pascals against the volume, meters cubed, then we know that P, according to Boyle's law, is proportional to 1 over V. So we get this relationship that comes out. Okay, superb. Now, if we were to drive in that piston, then we know that's going to cause a change in volume. We've seen it here. And what we're going to do is we're going to look at the product of the pressure and the change in volume. Let's work out pressure is a force over an area, and we have a change in volume. A volume divided by an area leaves us with a length, so it's a force times a length, which a force times a distance is going to be a work done. So what we're effectively saying is here, as we push the piston in, we are doing work on the gas. And ordinarily, that would increase the temperature of the gas. However, not in this case with Boyle's law, because we're keeping the temperature constant. So what we've done in effect is in driving that plunger to, say, a point here, the particles are now making more frequent collisions with the wall and increasing the pressure. So we've moved from this point and we've driven along to possibly this point here, arbitrary points. Okay, now, I'm sure you're all familiar that if you do this with a bike pump and you move back and forth, then the temperature of the gas increases. The internal energy of the gas, should we call it U? So U is the internal energy. Increases. So it's fair to say that the internal energy has an effect if we do work on the gas. Of course, another way of increasing the internal energy is just to heat the gas itself. So therefore we could just heat it as well. So therefore we have these two ways of increasing that internal energy of the gas. And when I say internal energy, I want you to think about, does the temperature of the gas increase? If so, then temperature being the average kinetic energy of the particles would imply that it's increased its energy. So temperature is increasing, internal energy is increasing. And you can do it in two ways. You can do it physically, or you can do it just by heat. And that gives rise to our first law of thermodynamics, saying the change in internal energy is equal to the heat. And then actually we're going to use a minus convention there. It could be a minus or a plus, suggesting whether the work's done on or taken out. However, physicists usually use minus, chemists usually use pluses. So there is our first law of thermodynamics. It's worth saying here as well that if the temperature of the gas were to rise, then our graph here would be higher up, vertically displaced. So this is temperature 1 and this is temperature 2, because we need to bear in mind that the universal gas law holds true. The temperature is higher, then the product of these will be higher as well. So essentially that's all we need to worry about. Thermodynamics is a huge topic, but we just need to work within those ideas into a few questions to see how we get on. So let's look at a first example. Oh, and I should just say here as well, as I bring it back down, if we look at the pressure times the change in volume, which is the work done, pressure multiplied volume would be the area under a graph, because it's pressure and the volume. So this area indicates the work that has been done. It's been done on the gas, because you need to think about that arrow there. as you've compressed it, so you have done work on it. Whereas let's imagine we take 2 points on this graph here, and the gas has been allowed to expand, then the work by the gas is the entire area, and I'll shade this the other way so you can see it's all of that area is the work done by the gas. And so whether it's on the gas or by the gas, that's where these symbols are very, very important down here. Right, let's give you the first example then. We're going to take a cycle. We're going to look at another pressure volume graph. We're looking at this to make it easy in times 10 to the 5, so in terms of atmospheres. And we're looking at the volume in times 10 to the minus 3 meters cubed. It just keeps the graph nice and tidy. And this time we have these two lines again built in. One of the temperatures, 340 Kelvin for line A. For line B, we're unsure of the temperature. But we are undergoing a cycle, and the cycle is between points Q and point P. Point S, which is directly down below, and point R. I've drawn it accurately, they should actually sit on the same line. And the line they sit on is at 0.75. This higher line here sits at 1.25 times 10 to the 5 pascals, of course. Their respective volumes are 2 times 10 to the minus 3 and 3 times 10 to the minus 3. Okay, first of all, first question is, how many moles of the gas are being used? You'll have to make use of this ideal gas equation again. So if we take the ideal gas equation and we rearrange it, then we can take a series of values from this graph here. We know it's sitting at 340 Kelvin, and we can take a volume and a pressure and work it out. So let's take, I forgot to mention what this point was running at here. This point was running at 0.5. This are obviously axes which don't come through 0, 0. So let's say we take our point. Let's take this point here at S. Let's take 0.5 times 10 to the 5. The pressure, the volume is going to be 3 times 10 to the minus 3, divided by the ideal gas constant and the 340 Kelvin. And that should give us, if I just tap it quickly into the calculator, just to make sure my maths is right. That's giving us 0.053 moles. Fantastic. Right, what about the second part? Well, let's think about what the temperature of line B is going to be. Okay, once again, we're going to use the ideal gas law again. We know the number of moles of gas which does not change, and we have a reading for the higher line. Let's take point Q, and we're going to say PV as nRT again. We continue to work it through, this time looking at the temperature of line B, which is PV over nR. P is going to be at point Q, is going to be 1.25 times 10 to the minus 5. Multiply that by 2 times 10 to the minus 3, which is the volume. Our newly found number of moles and our ideal gas equation. And that should come to 567 Kelvin. This is 567 Kelvin. Good. Now, the last thing we really want to do with respect to the graph is we would like to look at the work done in one cycle. i.e. imagining that the cycle moves in this direction. First of all, I suppose we should talk about what the cycle includes. Well, we have compressed a gas from point P to point Q at a fairly high temperature. Then we've allowed that gas to drop in pressure, though not change its volume, which must imply a cooling of sorts. We've compressed it again. No, sorry, we've let it expand, and it's increased its volume and its pressure is decreased. And then at a fixed volume, it must have raised pressure, it must have taken in some heat. So if you imagine this has been work physically, heat. No work done in these 2 points, only in those 2 points. So what's the work done in the cycle? Well, work done in the cycle is going to be the area under the line PQ, right at the bottom, minus the area under the line RS. So in actual fact, this area here is the work done in the cycle. Now luckily we've got some really nice points here that we're going to use, but let's work that out. If we have, so the work done, it's really going to be these two triangles. It's going to be this triangle here, assuming this is a triangle. You can assume it's a triangle. You could also, if you want, if this was a graph, count the number of squares inside and multiply by the energy per square. But I'm going to assume there's two triangles taking place. So looking at the first triangle, QPR, we've got a half times the height times the base, and the height is going to be the difference, which is 0.5 times 10 to the 5 by 1 times 10 to the minus 3, which is the base, and add that to, I'm going to do the same again, half times the height, which is 0.25, the pressure here, times by the base, which is the same again. When you bring that together, it comes out as 34.5 joules of energy. Okay, hope you can see that. Brilliant. There's just one more step which is very useful to use, and that is to work out in this point here where just heat is being transferred, this part of the line, you can start making use of the ideas of specific heat capacities, or should I say delta U. The energy change is going to be mass times specific heat capacity times the change in temperature, or indeed the number of moles by the specific heat capacity per mole by change in temperature. So what's happening here is for gases, liquids and solids, especially where there's no change in volume. But if a volume is held, then this equation holds true. So what we could say to ourselves here is, let me just draw a little, it's getting a bit cramped here, but let me just draw this bit in. If we know in this instance that 20 joules per mole per Kelvin are required to heat the gas, then what's the energy taken in at this point? Well, the energy is going to be the number of moles, we have that previously, 0.053, by obviously 20 joules, by the difference in the temperatures, 567 minus 340, and that will give us a change in temperature of 240 joules taken at this point. Okay, there's a lot to take in there. However, what we are dealing with is we are looking at specific heat capacities. We're looking at the ideal gas laws, and then finally we're thinking about how that energy of the gas is being changed, whether it's physical or whether it's by heat. Okay, if you're feeling quite confident, let's have another example. And you can try this one yourselves if you want, and then I can give you the solutions and see how it goes. So, another example. Okay, this time it's slightly different, the graph. It might be worth me talking through what's going on. Again, we have the pressure, just like before, and the volume, just like before. this time what happens is the gas is going to be allowed to, let me just make sure I've got these lines in properly. The gas is going to be allowed to expand but not lose its pressure at all, which is quite strange. I mean, how would that happen? Let me just put my little cylinder here so we can think about it. And you don't need to be too worried about how that would happen, but if this were to expand out, you'd imagine the pressure to drop. So really, the particles, in order to not reduce, must increase in speed, so it must mean that they must be taking in some heat. Then from point B to point C, we have a drop in pressure, though no change in volume. So at that point, heat must be removed from the system. So this is AB, whereas this is BC. And then it undergoes a compression from the movement C to A. So then you're undergoing no heat change at all, but the piston's moving in again. Okay, so there's our cycle. Let's put some numbers to it so we're familiar with what's going on. 23, 20, we have a lower point of 0.8 and a higher point of 1. So I suppose first of all, let's work out the number of moles. If you think you can do it, hit pause, give it a go, otherwise I'll work the solution straight away. Okay, then just from the previous one, we know this is going to be PV over RT. We have, should I have said before, actually, apologies, that point there is 323 Kelvin. So now if you want to press pause and give it a go, go for it. Okay, solution time. Okay, then, so we're going to take that point, and we know the pressure, we know the volume, we know the ideal gas constant, and finally we know the temperature, and that gives rise to 0.744 moles of gas that are present. Good, okay, and just to see if we're capable of it, what is that actually, how many molecules is that? If you want to give it a go, press pause, otherwise here we go. Actually, it's just the Avogadro's number multiplied by the number of moles. Avogadro's number is 6 times 10 to the 23. We've also got our number of moles, 744, giving us, I'll just type that into the calculator, yes, 4.5 approximately, times 10 to the 23 particles. Good. Right, what about the temperature? Now, here's the next one. What about the temperatures at point B and point C? Let's see if you can work out that. So let's do temperature at point B first, and then we will go on to work out the temperature at point C. If you think you can do it, go ahead. Otherwise, here comes the solution. Okay, there's two ways to do it. I'm going to put a box on this side just to remind you of this law that we did with gas laws, that pressure and volume in the first instance divided by the temperature is equal to the pressure and the volume in the second instance. So what you could say if you wanted is that you kept a constant pressure in this first transition. So the pressure you can ignore from both sides, and the change in volume is going to be the same as the change in temperature, and vice versa. Or you could go flying through again and using this brute force method we used before. Either way is perfectly acceptable. Let me go for the quick way. I can say that V1 over T1 is going to be the same as V2 over T2, because if I were to bring the pressures on the same side, let's imagine, just move pressure down there, they cancel out. So therefore, the new temperature is going to be the old temperature multiplied by the ratio of the volumes. And I don't have space to write it in there, but let me just, I have done previously, and that comes out as 371 Kelvin. What about the temperature at C? Well, this time I can ignore the volumes because it's a constant volume, so I can say the pressure is equal to ratio of temperatures. So I want the temperature at the second point. It's going to be the initial temperature multiplied by the change in the pressures. Yes, that's correct. And then that gives rise to approximately 296.5 Kelvin. I'm just double checking to make sure that is correct. Pretty sure it is, yes. Okay, so fairly straightforward in the first instances. Now this is the interesting point. Now we're going to look at B to C a bit more carefully, and we're going to say, and I said B to C meant heat is coming out of the system. Heat is coming out, no work is being done. What they've decided to do here is actually pour cold water on this cylinder once the piston had stopped moving at B to take the heat out. So let's imagine we did pour cold water on it, and there was cold water poured on. What's the temperature change of the water if you poured on 0.125 kilograms of water onto that cylinder? Once again, if you think you know, press pause, otherwise here comes the solution. Well, we once again use the change in internal energy as mass times specific heat times the change in temperature. And we pretty much know most of that. Let's rearrange the equation to get the change in temperature of the water, which is going to be the energy, mass times specific heat. Oh, apologies again, I should have told you that 715 joules of energy was extracted from the cylinder. And hopefully you know that that's the specific heat capacity of water. Joules per Kelvin per kilogram. Right, so if we had 715 joules extracted from the water, we've got 0.125 kilograms of it, and we know the specific heat capacity is, then that brings us to a 1.36 Kelvin change in temperature of the water. Excellent. So I suppose the last point really that I need to make reference to is the first law of thermodynamics, and really talk about what's going on here, in that these bits of the cycle have very distinct parts of increasing or decreasing the energy in the gas. This part is very distinctly a heat. This part is very distinctly a work, a physical aspect. And this part here is a combination of the two of them working. Throughout the entire thing, of course, the internal energy change of the gas is zero, because you're working it, then you're heating it, etc., etc. Right, hope you understood it. That's it.